Hey y'all, welcome back to another LeetCode video, problem 199. This problem is asked by Facebook or Meta. So we're given the root of a binary tree, and we're imagining yourself positioned on the right side of it, viewing all the nodes. So we have to return those values of the nodes that we see ordered top to bottom. So in this case, we're given our binary tree, and if we're viewing it from the right, we return nodes 1, 3, and 4. If we're given another binary tree of root 1, no left child, but there's a right child 3, then we just return 1 and 3. And obviously if you have no nodes, then we just return an empty array. So this problem solution when going to the approach is using something called a level order traversal or a breadth first search. So you'll see that if we're given our input of all the nodes in the binary tree, we kind of search it by level. So we have 3 right here, and then we have 9, 20, 15, and 7 correspondingly. And you'll see kind of this small pattern is that we have subarrays respective to the level that they're on. So 9 and 20 are on its same level, so we group them in an array inside of the array. 15 and 7 are in their own level, so we put them in an array, and 3 is on its own at the root on its own level. So that's one way that we're going to be going. So a breadth first search works like this. We start at our root node, and then we snake around. We go to 2, 3. We come around right here, 5, and 4. And that's how breadth first search or a level order traversal works. Okay, and the data structure that is associated with a breadth first search is a queue. So what we do is we start our root node, right? We start at 1. We enqueue it into our queue. And then we pop it out, and we're like, hey, does 1 have any left or right children nodes? Yes, it does. It has 2 and 3. So now we're going to enqueue 2 and 3 into our queue. 2 and 3. And we're going to do the same thing. So we're going to pop out 2 from our queue. We're going to dequeue it, and we're going to be like, hey, does 2 have any left or right children? Yes, it does. It has right children, but it doesn't have a left child. So now I'm going to enqueue that 5 into the queue. And then now I'm going to take this 3 that we have and be like, hey, does 3 have any left or right children? It has a right child. It doesn't have a left child. So then I'm just going to enqueue 4 into my queue. Does 5 have any children? No, it doesn't. So we pop it out, dequeue it. There's no children for 5. Does 4 have any children? No, it doesn't. So we just do that. And you see, I'm grouping them into the subarrays based on the level they are on right here. So they're kind of grouped in their own array, respective of the level. And if you notice, one thing is that the right elements, lastly, this is the last criteria to solve this problem, is that they're the last element in each of this index. So the last element in this index is 1, the last element in this index is 3, last element in this index is 4. So in each of their subarrays correspondingly. So that's one important thing to note. And once we do build our array of all the nodes that we have in our binary tree, what we can do is implement another data structure called a stack, where we can just append all the elements in the array that are the last element in it. So we just have 1, we'd have 3 in our stack, and lastly 4. And this would be our solution. We just output 1, 3, and 4. So now the code implementation for the solution. So I'm going to be importing this library called dequeue to make use of the queue data structure. And then for the case that there is no root, then we just can return an empty array. And now I can make a result array, which is going to have all the nodes in our binary tree. And then I'm going to be initializing our queue with dequeue filled with the root nodes. And then while we do have a queue, that means we're going to be running this while we do have a queue. We're going to have a current level, and this basically just initializes these subarrays based on the level, and then we're going to append it to the result array, which is the bigger overlapping array. You'll see in a moment. So we're going to have a current level, and then we're going to have a level size, which is going to be the length of the queue, the size of the queue. And then for each element in our level size, or each iteration in it, what we're going to do is we're going to pop our node, which is going to be q.pop left from the left side, and then we can add that to our current level that we're on, the value of it. And once we do that, if there's a left child, then we can add that to our queue. If there's a right child, we can also add that to our queue. And once we've done this process, we'll have our current levels done. We can just add that to our overall resulting array. And then we'll have our result array finished. So to give a demonstration, I'll just print the result right here. And you'll see it'll just build our array with also the corresponding levels that each of the nodes are on right here. And now for the last portion, to actually solve the problem and to return all right elements viewing from the right side. So to do that is we can just initialize an empty stack, or the result stack. No, I'll just name it stack. And we can iterate for I in the range of the length of result. What we're going to be doing is we're going to add that to our stack. The result at I of the last element, so accessing the last element with index -1. And then we can just return our stack. You can see it worked. Submit the solution. So yeah, that's how you do it.